As you begin working physics problems, perhaps from the back of the book or a worksheet or wherever the problems are going to come from, even in one-dimensional motion, you often deal with problems that have multiple accelerations in one problem, and you need to know how to deal with those. So what I'm going to do here is look at just a classic example. I'll sort of do this by way of example here. Suppose there's a car here driving down the road here, and there's a deer over here. So there's a deer sitting in the middle of the road here, and you're sort of humming along here with some speed, say v naught. That's your initial speed. And what the question typically asks for is as soon as you notice the deer there, you have a bit of reaction time. That's typically the time it takes you to get your foot onto the brake, and then you brake, and then you want to see if you can hit the deer or not. So there's could be a couple of acceleration zones, say, in this problem. Let's see if we can identify what they are. So during the reaction time here, I'll just say this is when you see the deer and you're moving your foot from the gas pedal to the brake. There's going to be a bit of reaction time in there. Say it takes you a bit of time to get your foot over there, and we can even estimate a number, maybe about a half a second, but it won't be important for what we're doing. So what we do is if we put a dotted line in here, we can say that all in this zone right here, the acceleration is 0. Why is it 0? Because we're going to maintain that speed while we take our foot from the gas and put it on the brake. The car is neither slowing down or speeding up, at least in the hypothetical here, and so that would be one acceleration zone. But what would happen there is, say, if we call this zone 1 right here, when the car reaches this boundary right here, say right where this dotted line is, what we're going to say then is we have the brake on. We have our foot on the brake, and the car is going to start slowing down. So the acceleration here might be some number like, let's say, 1 meter per second squared, or whatever number is given for how hard the car might be braking in the acceleration. Furthermore, since the car is moving this way, let me get into the zone here and draw another car for you. Since the car is moving this way, and we'd expect the braking acceleration to be back that way, we better call that minus 1 meter per second to stick with the sign convention. V is to the right, that's positive. A is to the left, that's negative. So see, we have another zone of acceleration here, even for the same car. And then what might happen, depending on what sort of problem you're working on, there might even be a third zone here where maybe you brake even harder or something because you realize you're about to hit the deer, so you really push the brake even farther, or maybe the road changes into gravel or something like that, that the acceleration can change once again, so we can have even another acceleration. Maybe we'll have even another one here. Maybe it gets a little higher because you really ram on the brakes, you don't want to hurt the poor deer. You can call it something like minus 2 meters per second, something like that. So again, multiple zones. Let's see what this might mean in terms of problem solving. Well, the first thing you should do is probably get a little more organized with it. Since this is zone 1, let's call it acceleration 1. This is zone 2 here, let's call it A2. And this is zone 3 here, so let's call it acceleration 3. So we have some nice labels for them all, and we know exactly what zones we're talking about. Now in terms of physics, how do these zones connect? Well, you know that the velocity that the car has coming out of zone 1, the final velocity in zone 1, will be the initial velocity in zone 2. So in other words, as this car goes from here to here, the initial velocity here, whatever velocity it has right as it hits this dotted line, is considered like the initial velocity it takes as it enters zone 2. And likewise, the same thing will happen over here. The final velocity it has in zone 2, so after this deceleration happens right here, will be the initial velocity it has as it enters zone 3. And these are the things you can use to plug into the equations to find distances or stopping distances or speeds or whatever the case may be. But again, whatever speed the car carries to this dotted line is the new speed it'll carry into this zone. And whatever speed the car had when it reaches this dotted line is the new speed it'll have as it goes into this zone right here. The positions also link up that way. So whatever distance it achieved when it reaches this first dotted line, so x1 here is going to be the new position in zone 2. So whatever position this is here is where this zone ended, but is where this zone began. And over here, the position it has as it enters zone 3 here will be, the position it has as it leaves zone 2 will be the new position it has as it enters zone 3. So as the car moves to this dotted line, it's done with this zone, but it's achieved this distance right here, but that will be the new position it has as it enters this zone here. So these multiple zone accelerations are best divvied up by some dotted lines to recognize, hey, I'm coasting here, I'm braking here, I'm braking even harder here, and by separating them out, you're able to keep the problem separate, solve for each zone separately, and then attack the problem according to what might be needed at that point. But that's definitely the way you handle multiple accelerations. You need to read the problem very carefully to determine them, because most problems will have 1 or 2 multiple acceleration zones, maybe even 3 if it's a complicated problem, and you need to be able to know how to tie it all together.